DNS cookies provide protection for queryers. That can be a stub resolver or a smart resolver, RDNS server. DNS cookies also provide protection for the domain name owner. Let's stop there and think about just those two. How is that done with a big picture? Well, there's something called a client cookie. And as long as the client cookie is present and supported by both the querier, the client, and the server, this protection is automatic. Nothing needed to be configured, just works. The other protection for the innocent and DNS servers, it's provided by something called a server cookie. And the server cookies come in addition to the client cookies. We'll talk about the difference of those coming up in the upcoming slides. That protection requires extra configuration in bind, but it's just one line of configuration and it works. Getting a little deeper into it. Cookie security is limited to off-path attacks. And in the picture shown, the attacker has either sniffed the traffic or was literally a router and received the traffic between the querier and the server. So as the query was going from the querier to the server or the other way from the server back to the querier, the proper answer was coming back, the attacker was able to sniff the traffic. That's an on-path attack, the one shown. If it's an on-path attack, cookies provide no security. Those attacks obviously require sitting in between the querier and the server, and tons of attacks don't require that. These are these off-path attacks. Cookies provide wonderful security for those. The cookie protection requires that both the querier and the server being sent the query support cookies. If one side or the other supports it, they're just ignored. They have nothing, they don't work at all, they don't do anything. Not an issue. Quick fact sheet about cookies. They are 64-bit pseudo-random values. The content for the pseudo-random generation is coming up on an upcoming slide. They require extended DNS, eDNS, because they are an OPT resource record. If you don't know what that means, you can look it up. There's other sources. Come to our courses. Servers do not have to store state for the clients. And that's a really big deal because that would be a big load on the client, on the server, excuse me. If the server needs to store information about every client's cookie, this would be a very heavy solution. But it's a light solution. It doesn't store any state or store any cookies at all. DNS cookies are not related to browser cookies, and the RFC 7873 from May of 2016 were the standardization. There's the name. All right, let's dig in. The next 7 slides will show how cookies are exchanged and used, coming from the query and the server back and forth, and how each one is thinking about it. After that, we'll look at actual queries being done using dig, and then a couple of dig options related to cookies, and after that, we'll look at how you can configure cookies in named. Okay, here we go. We have a query on the left, and he says, hey, I'm sending a query to server X. He looks in his cache, and he says, I don't have a cookie for that server. And so he generates a new client cookie. And the input for the pseudo-random function to generate the client cookie is his own IP address that he's sending the cookie from, the server's IP address, and a secret that the client self-generated, a random secret. And there goes the query. And in the additional section, we have an OPT resource record. So this is eDNS. And there's a client cookie option. What happens now? Well, the server says, well, that's a nice client cookie, but it doesn't do anything for my security. So what does the server do? He says, well, I'm going to generate a server cookie for that specific client. That's also a pseudo-random function to generate the server cookie. And the input is the client's IP address, the server's own random secret, and the client cookie. So he's going to send back the client cookie. That's part of what comes back. And now The server responds normally. So if it's NX domain, he says NX domain. If it is a positive answer, he sends an answer in the answer section. Totally normal response. But in the eDNS section, in an OPT resource record, he sends back both the server cookie and the client cookie. Now, that's actually an option. But this is what bind does by default. He sends back the client cookie and the newly generated server cookie. The server had another option, and we can configure this later in bind. We will. The server could have responded with a new response code called bad cookie. And if he had done that, he wouldn't have sent a normal answer. He would have just sent that, but he would have responded. And he would have sent, again, his new server cookie and the client cookie. Okay. He could have also dropped it if he thought that there was a rate limiting problem, but that's unrelated to what we're talking about here. Okay. So there is the bind standard, normal query response with an OPT record in the additional section containing the original client cookie and the newly generated server cookie. Now we're back at the querier. And the querier, forget about the server cookie. All the querier needs to do is look at the client cookie that just came back. If it's not valid, if it's not the client cookie that it sent, then it's not from the server. And he discards the response. That's all we need for the first two protections. That is enough to protect the querier from an off-path attack. Because if you're off-path, you didn't know that 64-byte client cookie. There's no way it was going to be guessed. I mean, I guess it could be, but it's very, very unlikely. It's basically impossible. So the client, the querier, has protected itself from getting a bogus response. And if it's an RDNS server, it's prevented cache poisoning. And the owner of the domain name has been protected as well. If that were proper answer, if the query had been for ripe.ca, well, ripe.ca, only valid answer is going to be, only an answer coming from the valid server is going to be accepted. Now we can also see as we're looking at this why this doesn't protect against on-path attacks. An on-path attacker would have seen the query, would have seen the client cookie, and would have been able to fake the client cookie sending back. That's why the security is only for off-path attacks. And this just worked. Nothing else was required. We've ignored the server cookie, we've configured nothing, and this just magically worked. And for attacks like the 2008 Dan Kaminsky attacks with random first labels, which were solved by port randomizations from the querier, which puts quite a load on the query. It slows down sending queries. Port randomization won't be needed when this is widely supported, when this is universally supported. So it will make things faster. This provides better protection than port randomization. But I'm getting ahead of myself. That's a whole other issue. For us right now, the client cookie alone provided all the protection. Querier sent it, he saw it come back, and therefore he knows it came from the server he sent it to. Now, what does the querier do? The querier caches the server's cookie. Now, don't forget, the querier may have gotten bad cookie. The server had an option. Bind doesn't do it by default, but the server could have said, I'm not sending you an answer, I'm sending bad cookie. You didn't send me a server cookie? I'm sending you bad cookie response. If that had happened, then the querier would have been disappointed. I didn't get a response, but he still got the server's cookie. And in that case, bad cookie, he would have simply requeried, again sending his client cookie, and again sending the server cookie. Because the server cookie was then present, in that case, the server would have responded. But that's still getting ahead of ourselves. So we've nailed it. We understand what the client cookie provides for us. And just as a reminder, server did not have to store the client's cookie. This is being done statelessly for the server. A little bit of time passes. The querier has another query to send to the same server. He looks in his cache and he says, aha, I have that server's server cookie. Now the query is sent, and this time it includes the client cookie and the server cookie. What happens on the server? Well, let's assume that the cookie is valid. Query arrives at the server containing a server cookie. Server looks at the cookie and says, in this case it's valid. That's great. It's the same cookie I sent that client. By the way, I didn't have to save state. I didn't have to save it because the client, the querier, sent his client cookie and I see his IP address and I know my secret. I can regenerate my server cookie. I compare it to the server cookie that arrived in the query. And if they're the same, I know it's a valid client. The client IP address was not spoofed. This is not an attack. Server will ignore any other defenses it has set up, since it's response rate limiting, can respond quicker, and it sends a completely normal response, NX domain, no data, no error, positive answer, referral, totally normal response, and sends the client and server cookie again. Server cookie is probably going to be the same, but if it happens to be that the server has generated a new secret in between, it sends its newly generated server cookie based on that secret. What happens if the server cookie is invalid? Now the server has a problem. There are several reasons that the server cookie that just arrived in the query could be invalid, and it has to figure out why. It's like, oh no, why is it invalid? Well, look, maybe its secret changed. Yeah, well, my secret did change, but I've saved my last several secrets, and I've run the algorithm to pseudo-random generation, and none of those old server secrets generate the proper server cookie. This is spoofing. Well, maybe not. Maybe the server doesn't have the proper old server secret to generate the cookie. It's unlikely, but it's possible. In that case, it's not spoofing. There's a whole other possibility. If the client changed its secret, which means it would have changed its cookie, then the server cookie wouldn't match up with that either. And again, it's not spoofed. The client just changed its secret, changed its cookie. And additionally, if the client is one of several machines with the same IP address, meaning it's part of an anycast system, then it needs to be specially configured with the same cookie, the same secret. Otherwise, things will not work. That's a configuration error. Anycasting is beyond the scope of this, so let's ignore that. And then there's the fourth and last possibility. Maybe the reason the server cookie is invalid is that the client IP address is being spoofed. Maybe this is a reflection amplification attack, a distributive denial of service attack. So now, what does he do? He's got all these possibilities. Well, the server has the exact same options as at the very beginning when there was no server cookie present, only a client cookie. The server can respond with bad cookie. Bind does not do that, not by default. What bind does is totally responds normally, gives a positive answer, referral, NX domain, as if he doesn't care that there could be a spoofed IP address. Why? Well, because he's not configured for the protection that would provide this kind of protection for himself. So this attack, if it is a spoofed IP address, this is that third and fourth type of attack we looked at the beginning, where the attack could be causing a denial of service against the server itself, but without configuration, he's not going to do anything. And the server may be part of a reflection attack. And again, he's not going to do anything unless he's configured to set bad cookie. Bind doesn't do that by default, not today. Okay. So what happens? It's an invalid cookie. What does the server do? Just responds normally, but it sends back the valid server cookie. So the next time the querier sends a query, he should, assuming it's the real client, use the proper server cookie. So in any of the first cases, client's cookie changed or the server's secret had changed, this problem would only happen once. Okay, so we have the fundamentals. Let's look deeper. If you're interested in our training, the URL menandmice.com/training is on the screen. Thank you for watching this video on DNS cookies.